Welcome back to my course Aspects of Biochemical Engineering. In the last lecture, I started the kinetics of homogeneous chemical reactions, and as I mentioned that before we understand the biochemical reaction engineering, we should have some kind of thorough idea on the chemical reaction engineering. And in the last lecture, I try to concentrate on that what are the different classifications of the chemical reaction. I told you that whatever chemical reactions we have, broadly it can be divided into two different classes. One is called homogeneous reaction, another is the heterogeneous reaction. Now, in case of homogeneous reaction, the reaction takes place in one particular phase. As you know, we have three different phases. One is gas, liquid and solid. Now, when the homogeneous reaction takes place, mostly this takes place either gas or liquid phase. In the pure solid phase reaction is rarely available. Now, in case of heterogeneous reaction, that more than one phase present there, either gas liquid or liquid solid, the more than one phase should be present in the reaction mixture. So, bottlenecks of this particular heterogeneous reaction is that one phase has to diffuse to the surface of the other phase, and then and only then the reaction takes place. And after the reaction is over, the whatever product is formed, the product supposed to diffuse from the surface of the other phase to the and diffuse to the next phase. Now, so diffusion is a diffusion as well as reaction, both we shall have to consider in case of heterogeneous reaction. Now, if your rate of diffusion is less than as compared to rate of reaction, then diffusion will be the controlling factor. Now, in case of rate of reaction is less as compared to rate of diffusion, then rate of reaction is a controlling factor. Then I try to we talk about some kind of mathematical modeling. Mathematical modeling is the mathematical representation of the process. Now, we started with some kind of chemical reaction. In the chemical reaction, we try to write the reaction kinetics equation, and this equation, rate equations, is kind of modeling. And today in the last class I tried to discuss about the irreversible reaction, how we can analyze. In addition to that, we also discussed the parallel reaction, also autocatalytic reaction, which is largely applicable in the biological system. Now, today I am going to concentrate on two different reactions. One is called steps before the glucose is converted to pyruvic acid. Now, and if you look at the individual steps, all the steps more or less they are reversible in nature. So, from this metabolic pathway, we understand the biochemical reactions they are mostly the chain reaction, that is 8, 1, 2, 3, 4, the 10 different steps are involved before we get the pyruvic acid. 1 mole of pyruvic acid produces 2 moles of 1 mole of glucose produces 2 moles of pyruvic acid. Now, if you look at the individual steps, we will find they are reversible in nature. So, in the biological system, we have both chain reaction as well as the reversible reaction. Today, I want to discuss both the chain reaction and the reversible reactions. Now, if you look at irreversible chain reaction, what we have seen in the glucose metabolic pathway, the tail steps are involved because before the glucose is converted to pyruvic acid. Now, here we have taken one instance that A to B, B to C, C to D, D to E. The different products that we have and intermediate product, that is B, C, D we have. Now, if you look at that concentration profile of the different component present in the chain reaction is like this. If you look the first component A, that is keep on decreasing with respect to time, and last component E, if you see, that is keep on increasing with respect to time. But all intermediate compound like B, C, D, they're rising then decreasing, rising and decreasing. The one thing I want to emphasize here, then until unless B forms, C cannot be formed. Until unless C formed, D cannot be formed. That is very important. So in case of this intermediate chain reaction, that the strategy is that first component, that substrate will keep on decreasing with respect to time, and last component to keep on rising with respect to time. All intermediate compounds, they will increase then decrease. So this is the how this reaction looks. Now let us consider a very simple chain reaction that we have. Let me consider a very simple that reaction, that is A to B, B to C. This is kind of irreversible, that simplest chain reaction that we have. Let us assume this is the rate constant is K1, and in this step the rate constant is K2. Now if you want to write the rate of substrate degradation dCA by dt, this will come around K1 into Ca, if you consider the first order kinetics. Now if you want to write Cv by rate of formation of the intermediate compounds, then this will be what? Rate of formation K1 into rate of formation of A, and P also degraded to C. So this will be K2 into Cb. Now if you want to, this we can consider number 1 equation, this we consider number 2 equation, and another is dCc by dt. This will be equal to K2 into Cb. So this is 3 equation. Now here, if you want to draw a profile of the 3 component present in the reaction mixture, so I showed you in the chain reaction, the first component Ca will keep on decreasing with respect to time, and B, this will increase and then will decrease, this is the Cb, and last component will keep on increasing with respect to time, that is Cc. Now here what we are interested to develop the equation for Ca, then Cb, then Cc. So introduce the equation how we can correlate with respect to time, so that if we put the time that in that equation we can get the respective value. Then I forgot to mention in the last class, there is another term called the simulation, that because when we write any kind of model, suppose we have written this model, we determine the value of K1 after I showed you how K1 and N value can be determined. Then when you put these values there, then we can simulate the we can solve this equation, and we can develop the theoretical correlation between the concentration of substrate with respect to time, and then we compared with the experimental results. And when you compare with the experimental results, we try to calculate what is the percentage deviation of these results, and if the percentage deviation is less than 5%, then it is acceptable. If more than 5%, then we do certain modification of this equation. Now next step, that if you look at this equation, what I have written before, then what I did, dCA by dt equal to K1 into Ca. Now I can write this is dCA by Ca, this is equal to K1 into dt, this we can write. Now this is equal to d ln Ca, and this is minus K1 into dt. Now if you do the integration, this is Ca0 to Ca, and this is 0 to t, then what we will get, this is ln minus ln Ca by Ca0, this is equal to K1 into t. Am I right? Now this equation I can write in this form, A equal to Ca0 into e to the power minus K1t. So because Ca0 is constant and K1 is a constant. Now in this equation, if you put the value of t, because 1 minute, 2 minutes, 3 minutes, whatever value respect. So what we have, what I wanted to mean, so we have experimentally we have developed the equation with respect to time. Suppose this is the experimental value, then then in the theoretical theoretical value also we can find out here what is the respective value we can find out, and then we can easily calculate what is the percentage deviation we have as with respect to the experimental result. From that we can write the validity of the particular equation. So this is number 4 equation that we have. We should remember that. Now next next you can remember I told you Cv by dt Ct is equal to K1 into Ca minus K2 into Cv. Am I right? I have written K1 into Ca minus K2 into Cv. So this I can rearrange like dCv by dt plus K2 into Cv. This is equal to K1 into Ca. Now both sides, if you multiply it by e to the power K2t, e to the power K2t, and this is e to the power K2t, then what equation we will get? Here we can write this as dCv into e to the power K2t by dt. I can write like this, and here this is also, here we have done some mistake. Here it will be already K1 is there. This we can write K1 and multiplied by K minus 1 was there, and into multiplied by e to the power K2t, because we multiply both sides by e to the power K2t. So this I can write K1 Ca e to the power K2 minus K1 into t. This we can write. Now this equation, from this equation we can write Cb into e to the power K2t. This should be equal to what? This should be equal to K1 into, this is Ca0, this is Ca0, Ca0 is a constant, and this is K2 minus K1, and this is e to the power K2 minus K1 into t. This we can write this plus constant. Now we have the boundary condition. What is the boundary condition? At t equal to 0, Cb should be equal to 0, because until unless A degraded, that B cannot be formed. If it is that, I can assume this. Now if you assume the Cb equal to 0, this first portion will be 0. Then here if you put t equal to 0, then this will be 0. So what we can write, the constant equal to minus K1 Ca0 into K2 minus K1. This we can write. Now this equation I can put it here. This is constant. Now I can erase this. I can take it out, and I can put this value here. That this also I can remove, and here we can put minus, this is K1 Ca0 K2 minus K1. This I can write. Now once, so your equation, what is the equation? You have Cb into e to the power K2t equal to this. Now if you divide this side with e to the power K2t, then what will get? You will get Cb equal to Ca0 divided by K1 K2 minus K2 minus K1. Here you can find out e to the power K1t minus e to the power K2t. You can find it out. Now, the another thing is that, and here, and then we can calculate that now we have seen that the CB versus T, what is the profile that you have? It is like this. Now we are interested to calculate the value of this point. What is this point? This point CB will be maximum. So this we call T max. So at this point dCB by dt, because this attains the plateau, so this will be equal to 0. So now if you differentiate this CB by dt, then what you will get? CA0 minus K2 minus K1. Now here I can write, most probably here we have K1, and here minus K1 e to the power K1t plus K2 e to the power K2t. Now what we can write, this is again it is K1. So what we can write, this will be equal to 0. Now this cannot be equal to 0, so I can assume this is equal to 0. Now if you put this equal to 0, what you can write? The K1 by K2, K1 by K2 equal to what? Equal to, I can write e to the power K2t by e to the power K minus 1t. Am I right? So if you take it up, what you will get? E to the power K1 minus K2t. This we can write. This is K2. Then this is, if you take log, then K1 by K2 equal to K1 minus K2 into T. Now here the T you can write, T equal to what? T equal to 1 by K1 minus K2 ln K1 by K2. So we can, this is equal to T max, because this is the time. You can easily, now in this equation, if this value, T max value you put here, we get the CB max value. Then we can easily calculate the CB max value. This is how you can find out the time at which we can get the maximum intermediate product formation. Now here we have shown in this particular slide, you can see this is A to B, B to C. Now that is the rate of degradation of A. This is minus, this minus I can take it here. This is K1 into Ca. Then rate of formation of B, I can write this, and rate of formation of C, I can write this. Now here we know that the total concentration, initial concentration of A would be equal to concentration of at any point of time. This is the equimolecular conversion. The equimolecular conversion means 1 mole of A converted to A, 1 mole of B, 1 mole of B converted to 1 mole of C. So I can write Ca0 equal to Ca plus Cb plus Cc. This we can write. Now from the first equation, we have seen that this is dCA ln Ca by Ca0 equal to K. This is equal to this. I have already shown you how we got this. Now in case of intermediate product formation, this is again, this is equal to this dCB by dt equal to this. This I have already shown, and then we bring it here. Then we finally write the equation like this. Now when you do the differentiation of this, then finally we come across this equation dCB into e to the power K2t equal to K1 by K2 minus K1 Ca0 e to the power K2 minus K1t plus constant. Now we put the boundary condition at t equal to 0, Cb equal to 0, then the constant value will be this much. Then finally we have come across this equation. I showed you the Cb equal to K1 Ca0 K2 minus K1 e to the power minus K1t minus e to the power K2t. this we can get. And this is so in this equation, if you look at that, everything is constant. K1 is constant, K2 is constant, so Ca0 is constant. So if you put the time t, then you can easily find out, we can easily find out the correlation between Cv versus t. You can have the, this is called theoretical correlation, that you can easily find it out, that if you put the at different time, just you put the time value, you will get the value of Cv here. Now this is, I showed you that once you get this equation, if you want to find out Cv max, you can easily do that at this at Cv max, dCv by dt equal to 0. If we differentiate, we will get this. Now here you see that this is the equation I have already derived, and that ultimate, if you take it at the bottom, this is, we can write T max equal to k into k log min. This is this equation we can write like this. Now our final equation is coming like this. When we put the Cv max value in this equation, we get this Cv max equal to, we put the value, we can easily find out what is the Cv max value, we can easily calculate. So with this equation we can, now I told you regarding the Cc, we can also do it very easily, because I told you Ca0 is equal to what? Ca plus Cb plus Cc, am I right? Now what will be Cc value? This will be Ca0 minus Ca minus Cb. So we have already determined the expression for Ca, already we have determined the expression of B. So if we put this equation here, we can easily find out the Cc value. So we can, what we have done, Cc with respect to time, this is how it is increasing. This we can easily we can easily find out that if you put this equation. Now this is T max value, already we have calculated. Now Cr max, that equation we have shown you that T max value, we put that. Now this T max value we can substitute there, and we can get this equation. Then finally we get this. If you simplify this, it will come this equation. This final equation is here. You see that Cv max, and so everything is constant. You put everything in the form of constant, so you can find out, we can put the value, we can find out the Cr max value or Cv max value, we can easily calculate. This is, though we have written Cv max, this should be Cb max. So you can make the correction. Now this is how we can write, and this is final equation. Rearranging, we can get this equation. Now as I pointed out that most of the biochemical reaction, they are reversible in nature. Reversible means you can see there is a forward reaction, there is a backward reaction. So it is like this. If I write like this, this is K1, this is K2, and this is R. So at the equilibrium condition, rate of forward reaction should be equal to rate of backward reaction. What is the rate of forward reaction? K1 into Ca, K1 into Ca equal to K2 into Cr. So now Cr by Ca equal to K1 by K2, and this is nothing but equal to Kc, that equilibrium constant. This is the equilibrium constant, how we can calculate. Now in this equation also we can show that the equation is, this is very simple. The rate of formation of R equal to rate of degradation of A. This is can be represented like this. How this can be represented, we have shown you that what is Ca? Ca equal to Ca0 into Xa. What is Xa? The fraction of Xa, that is no, this is, sorry, this is not the right thing. This is, I can cancel. This will be 1 minus Xa. Xa is the fraction converted. So what is the fraction remaining? That is 1 minus Xa. That is fraction remaining. That is equal to Ca. Now if you do Ca, this will be what? Minus, this will be constant. So I can write Ca0 into dxa. So this equation, if you differentiate, this is constant. So this equation I can write in this form, dxa by dt, and this is equal to same. And what is Ca? Ca equal to Ca0 into fraction that is converted. And what is the Cr? Cr is this is equal to usually 0, and this is the fraction that remain. How much things has been converted? Ca0 into Xa. So at the equilibrium condition, this will be equal to 0. So we can write this, and E stands for the equilibrium concentration. So we can just change this in terms of equilibrium concentration. We can write this equation like this. Now finally, we from this previous equation, if you look at this equation, I can take Ca common, all these equations. So I can take out the Ca out, and this is equal to 0. Now the ratio of this, that m plus xae divided by this equal to k1 by k2, and that is nothing but equal to the kc, is the what you call your equilibrium constant. Now rearranging this equation, we can write in this form, we can write in this form, and then we can elaborate this equation in this form. This is very simple. We can do we can take this common, and when we write this equation like this, and finally we have the expression like this. When we have this expression, then we can plot this ln 1 minus xa, this versus this t. If you plot, the slope will give you the value of this one. Slope will give you the value of this one. So this is m equal to Cb0 by Ca0, that is constant, and xae is that conversion of under equilibrium condition. So if you put that value, you can easily find out the value of k1. So this is how you can find out the rate constant value. So in conclusion, what I want to tell that today I try to discuss that two type of reaction that is largely in operation in the biochemical system. One is the chain reaction, another is the reversible reaction. And chain reaction, we consider very simple chain reaction A to B, B to C, and reversible reaction A to B, how reversibly converted. Only one thing I forgot to mention, that that in case of reversible reaction, that we can increase the product formation by two different approach. Either you as soon as your Kc equal to concentration of product divided by concentration of substrate. Now if you want to increase the product formation, as soon as product form, if you take it out, more substrate will convert it into product. Or there is another approach we can have. If we add more substrate to the system, you will get more product because Kc remain constant. And in the chain reaction, we try to find out the time, the expression for all the different component present in the chain reaction. And major thing is that we are interested to find out at what time you will get the maximum intermediate product formation. Thank you very much.